Lately, front cover of the Times on Sunday. Anybody see the Sunday paper? That's right, you guys don't read the papers. They're free over there. You can go pick them up free. Sunday paper, the headline was, "Nosocomial infections are not required by hospitals to be reported." Glad to see the papers getting interested in this third leading cause of death in the United States, costing hundreds of thousands of lives a year. If terrorists were doing it to us, it'd be like on the cover, it would be the first subject of the, 100,000 people killed by bioterrorists this year. That would be a huge problem. If 100 people were killed, it'd be a huge issue. 3,000 people were killed on 9/11. It was a big story. All right, here's a picture that illustrates. You can probably see it better if I turn off the light here. That was on the cover. Also, of course, we were talking about Star Wars. And anybody go to the Star Wars convention over at Anaheim? They had like an expo, Star Wars. Seen the trailer for the new Star Wars movie coming out? I posted a link to it, so if you haven't seen it, you can see it. So we'll see what they do with that. So here's a fixation point. So the person looks at the fixation point. We flash two pictures. Here's another version of the diagram that we went over. Get a little more of it onto the screen at once.
You could pull it down.
They put the, what?
You could pull the screen down.
Pull the screen down, well, we got all we need now. The optic chiasm should be moved forward, so this artwork is a little bit deficient. Notice what's in the right visual field. They're putting the, every ray of light goes through a point in the front of the eyeball. I'll talk more about the pinhole model for representing the optics of the eye. So what's in the right visual field ends up over here on this side. They come together at the optic chiasm. These cross, so the paintbrush that's in the right visual field crossed over here. The lateral geniculate nucleus, there's another couple structures here that are also involved, and then fibers that come up to the visual cortex. So the visual cortex in the left hemisphere saw what was in the right visual field, and speech is over here in the left hemisphere. So if you ask the person what did you see, they'd say the paintbrush. If you say point with your right hand, they point to the paintbrush. They point with your left hand. The right hemisphere saw what was in the left visual field. Because the bird is projected over here on this side and this side. You can come to the optic chiasm here. These cross. And so what's in the left visual field ends up in the right hemisphere, which is connected to the left hand, which can point. So you need to remember, both hemispheres understand speech. The left hemisphere does the talking and is better at speech. So questions involving speech, you ask yourself, what did the left hemisphere know? The right side of the body is connected to the left side of the brain. The right side of the brain is connected to the left side of the body. Left hand, left foot, left cheek, left side of the body. All right? Any questions about that? Here's another example. Person fixates on the dot. We flash keychain. Ask them, what did you see? What would they say? Everybody all at once? They're going to see chain. And point with your right hand. Point with your left hand. All right, so that's what's being explained here from this diagram. Ask the person what they saw. They say chain. Point with your left hand to what you saw. They're pointing to the key. All right. So you're sure to be asked some questions like this on the final exam, as are all the other students taking intro psych this semester. Okay, so we're studying the problems of the topic area of sensation. And sensation is the study of the physics and physiology by which you know about the existence of the world out there. So vibrations in the air, those things influence sounds. Talked about the drum head last time and the vibrations in the air that you can detect through the mechanism in the ear. We're going to be talking more about this. So that's called audition, is the sensory capability to detect the vibrations in the air. Light, we're going to talk about light a bit. Light could be thought of as particles, could be thought about as waves. We'll say more about that in a bit. Contact, touch or cutaneous sensations, proprioceptive sensations, dealing with figuring out where you are, what's touching you, also temperature of the skin and sharp things that might be itching you and causing you pain. Chemicals in the air influence olfaction, food chemistry, salty or acidic foods might taste salty or sweet. So that's called gustation, the sense of both the combination of smell and, so the chemicals in the air and the chemicals that are on the tongue combined produce flavors. So the perception of flavors produced by sort of a combination of what you can smell and what's in your mouth. Those are the classic senses. Those are the senses that Aristotle talked about, the 5 classic senses. He also talked about a 6th sense, a common sense, but there are other sensory apparatus in the body. So position with respect to gravity, I talked about the vestibular organ last time that allows you to detect where you are in space. That isn't the whole story, as you know, if you've done the Star Tours exhibit at, I call it an exhibit or ride at Disneyland. How many of you have done the Star Tours ride at Disneyland? You're already aware of this. Those ships don't go anywhere, right? It's just an illusion. And yet you feel like you're being accelerated suddenly, and being accelerated partly because of vision and partly because they give you a little shove in the back. So the combination of the feeling that the chair is pushing against you in the back and what you see visually can make people feel sort of dizzy and also feel like they're flying through space. You pull up while driving your car and the bus next to you begins to pull forward. You may feel like your car is going backwards. So your sense of position in space is also influenced by vision as well as by the vestibular organ. So your sense of position in space. But even in a dark room, they could put you in a chair with no visual sensation and tip you to the side, and you'd be able to judge your position, your angle, if that chair is being tipped relative to space by the vestibular organ. And temperature, we talked about the temperature of the bloodstream being detected in the hypothalamus, and also there's heat and cold detectors in the skin and detectors in the hypothalamus of various components of the blood chemistry, like not enough oxygen, too much carbon dioxide, too much lactic acid, not enough sugar level in the blood. So things that people perceive as hunger or other things are being detected in the hypothalamus. And the hypothalamus also has detectors that are detecting hormones in the body so that the brain can communicate with the sex organs, for example, stimulating the hormones like steroids are being detected in the hypothalamus, telling the pituitary gland to release other hormones that may stimulate bone growth, repair of muscle tissue, the development of eggs in the case of the menstrual cycle, follicle stimulating hormone, various other. So the menstrual cycle is being governed and being detected. And it's through the use of the detection that you have birth control devices in the hypothalamus. So those are some other sensory apparatus. There are some analogies between vision and audition that we can talk about. And so we can talk about sound as we did last time, having a wavelength and an amplitude. So let's just talk about that for a second again. we've got our guitar string here. And the guitar string can vibrate. So we pluck the string and it goes this way and then back this way, and it compresses and rarefies the air, and it sends a waveform through the air. This is called the wavelength. And the height of this is called the amplitude. Now the guitar string also vibrates in halves. So the string can also vibrate this way, so it can go this direction, and then vibrate this way, and that creates what's sometimes called an overtone. It can also vibrate in thirds and in fourths. And so we can create a single string can produce a fairly complicated waveform. We can analyze that waveform by mathematics known as Fourier analysis. And Fourier analysis analyzes a complex waveform into its wavelengths and plots the amplitude of each wavelength as a function of the wavelength. So this is known as Fourier analysis. And so human speech is incredibly complicated. If you've seen an oscilloscope registering the waveforms created by human speech, it's a fairly complicated waveform, but it can be broken up into this pattern. Now, a single line would be a pure single sine wave. So if we had such an instrument that could create such a thing, not this guitar string, which is complicated, but some instrument that could create just a single wave, it would look like this. Let's say it creates 440 hertz tone. So 440 hertz tone, that's the A above middle C on the piano. That's the note that the violins tune to before the concert, although the French will tune to 444 because they think they're sharp. All right. Now the guitar string plucking a 440 or plucking a 220 may generate a 220, and it may generate a 440 and an 880. So these are octaves, but it would generate a pattern of overtones. And this pattern of overtones creates a complex combination wave that allows you to distinguish the sound of a guitar string from a violin string, or from another instrument, a piano playing the same note, or a person singing the same note. So human voice, a violin, a guitar, the guitar also differs in that it's plucked, and so it has a different kind of pattern of its onset. This is described as the envelope. But the fundamental frequency tells you what the pitch is going to be, and the pattern of overtones produces what's known as the timbre or timbre, depending on how you like to pronounce it. Now, in sound, the wavelength determines the pitch. The longer the string, the longer the wavelength, the lower the frequency. So the bigger the wavelength, the lower the frequency, the lower the pitch. So lower notes have fewer cycles per second and longer wavelength. Higher, shorter strings, if I take the same guitar string and I cut it in half, I go up by an octave. If I cut it in thirds, I get the fifth note in the musical scale, which is a harmonious note. That's something noticed by Pythagoras several thousand years ago. And he had a theory that integer ratios were particularly harmonious in terms of lengths of the strings that could be plucked. And the amplitude corresponds to loudness. So the wavelength, we also have a third quality that we could talk about, which is the timbre of the sound. So the more complicated waveform produces. So we've got qualities of sound, pitch, or the tone, the note that's being played, the loudness, and the quality or timbre of the instrument. We've got the same things in light. And so light can be thought of as particles, but it can also be thought of as waves and wavelength. Sir Isaac Newton was sent to the countryside because they were afraid of not measles, which is in the news today, not smallpox, which has been eliminated by vaccination, but the great pox. You know what the great pox was? Great pox was spreading at college campuses. Syphilis. And there was an epidemic of syphilis on the college campus. They said to Newton, who was, like 19 years old at the time, we better keep you out of school this year because of the great pox. They didn't really know exactly how it was spread in those days, but they knew it was being transmitted among the people that went to college tended to get it. Here on our campus, we have more chlamydia than we do the great pox, syphilis. Even though it was predicted with antibiotics it would be wiped out and be a thing of the past, it's still with us. So he was there by himself, and they didn't have television, fortunately, so he decided to let a beam of light through the window and put it through a prism, and this beam of light could be spread out into the colors. Red, orange, yellow, green, blue, indigo, and violet. So he was able to break up white light, sunlight, into a spectrum of colors. And he put another prism there, pointed the other way, and he could recombine all the colors back into white light. So he could separate white light into the colors, and you could take all the colors and put them back together again and make white light. Now if he got a sheet of paper or a sheet of something with a hole in it and let only the red light through and put it through another prism, it didn't change color. So it wasn't that the prism was changing the colors and distorting them somehow, it was separating them out. And Newton had a particle theory of light, and later people came up with a wave theory of light, and it turns out that both theories have been confirmed by experiments. So people think light has both properties of particles and properties of waves. It's one of the puzzles of talk when you talk about light. But light can be thought of as differing in wavelengths. I will tell you about the experiments where you can show that red light that's a little out of phase, so you take it based on the wavelength, you can predict where it's going to cancel itself out or not. So it creates interference patterns that can be used to measure the wavelengths of the light. So wavelength in light corresponds to hue, and amplitude in light corresponds to brightness. So many people have created Miller analogies. Do you know what a Miller analogies is? Miller analogies is a test that, 1 is to 2 as 2 is to blank. So 1 is to 2 as 2 is to what? 1 is to 2 as 2 is to what? If you were taking them out in 4, right? Because 1 is half of 2 and 2 is half of 4. So wavelength is to hue as wavelength is to pitch, or hue is to pitch as wavelength is to wavelength, or hue is to pitch as brightness is to loudness. So any parallelogram in this space creates an analogy, and they like to ask questions on things like the test of mastery of psychology and the graduate record exam based on questions like this. Now, one of the questions that was asked, and you read about this in chapter 1 of CALET already, telling a bit about the history of psychology, is can you measure the connection between physical measurements and psychological measurements? This was originally thought of by Gustav Fechner in the morning of October 22nd, 1850, when he was in bed wondering how come people hadn't paid attention to his 7 books on the mind-body problem in philosophy. He was a physics professor, and he was interested in the mind-body problem, and it occurred to him if he could measure the connection between physics and psychology, why he would call that psychophysics. And that would be the beginning of the possibility of a scientific psychology. And so from 1850 to 1860, he lifted weights. Not big ones, but little ones. And he judged how heavy they were. And he drew up the connection between psychological heaviness and physical heaviness. And he concluded that it was a logarithmic function. And so this became known as Fechner's law. And it was that the psychological value is a linear function of the log of the physical value, where phi is the physical measurement and psi is the psychological measurement. And he was able to deduce it from a physiologist who was studying sensation in physiology and was asking such questions as, how much do you have to turn up the lights for people just to notice the difference? How much louder does a tone have to be for people just to be able to discriminate the difference? How much warmer does it have to be for people to notice that you've increased the warmness in the room? And it turns out that equal physical ratios can be detected. So if you were judging a 100-gram weight, you can make, 100 grams is like about 20 nickels. So if people were judging the heaviness of a 100-gram weight, if you add 5 grams to it, people can just tell the difference. But if it's a 1,000-gram weight, you have to add 50 grams to it for people to be able to tell the difference. And the log function just happens to have the property that equal physical ratios correspond to equal psychological differences. If you've had one of those bulbs, like old-fashioned kind of bulbs that are being phased out these days, the incandescent light bulbs, that had a three-way switch, 50, 100, and 150 watts, right? Anybody had one of those? Well, the first thing, from a dark room to turning it on, that makes the biggest psychological difference. So the first 50 watts gives you the biggest difference in brightness. Then the next one is a pretty good increase in brightness, but not as big, up to 100. Then the next one is the least. So as you increase by 50 watts, each physical change gets to be less and less. And that's the property of the logarithmic function. So logarithmic function, if psi is a log function of phi, a given physical increase as you go up the scale becomes psychologically smaller and smaller. So 1860, Fechner publishes Elements of Psychophysics. He begins to lobby that Leipzig, University of Leipzig, where he was at the time, should hire somebody and give them a new title. We'll hire a professor and call him Professor of Psychology. There had never been such a thing before. So he lobbied the administration from 1860 till 1879, finally convinced them to hire Wilhelm Wundt. In 1879, they opened the first department of psychology. They hired Wilhelm Wundt to be the first professor of psychology who was studying questions dealing with perception, sensation, and perception. So Gustav Fechner, physicist, he was a strange guy. He got interested in these problems of psychology and perception. He wanted to get after images, and he used a method you should never use. He was looking at the sun to get after images. He caused himself damage to his retina. The damage to the retina, if you know something about the visual system, which we're going to learn about today, damage to the retina can produce damage in the brain, and damage to the brain can produce other damage in the brain. And so he developed a real problem. He couldn't stand the light, and he wasn't able to speak for a while, and he stopped eating, and he was being kept in a completely dark room, and he couldn't stand the light, and people thought he was going to waste away and die. And a servant girl in the household had a dream. And in her dream, she said, if we take some urine and beer and honey and mix it together and mash it together and make a kind of baby food out of it, he would eat that. So they mixed it up. History doesn't record whose urine it was. They mixed this stuff together and they fed it to him, and he ate it and he recovered. And later they asked him, you weren't speaking. He says, yes, I was thinking, but I just couldn't find any space between the words. So he had worked on the Wheatstone Bridge and other problems in measurement that you'll read about if you take a course in engineering or electronics. That was his field in physics. That's something about the beginning of Now we can look at a couple properties of light. Let's take a look at light is part of the electromagnetic spectrum. And these colors don't do justice to the actual colors of the rainbow. So when Newton spread out the colors and got the red, orange, yellow, green, blue, indigo, and violet. They didn't even try to draw the indigo and violet on there. Now we have new colors. As soon as I turn off the lights, right? So that changes it. I recommend you get some Austrian crystal, like from Swarovski Corporation, even though they make a lot of really expensive items, and it's a very pretentious company. Lee and I visited their factory, or actually their showroom over in Austria near the town of Hall in Tyrol. But they make the Austrian crystal, which is leaded glass and is intentionally designed to do what most optics are designed not to do, which is separate the colors out. So by adding lead to the glass, you can spread the colors out even more, and so the stuff looks sparkly and makes for nice jewelry and other decorative items. And they make a lot of decorative items, but just get a simple, maybe at CVS drugstore, you can get a simple octagon. They sometimes come with a little hole drilled in them. You can hang them on a thread, like a little piece of fishing line or a thread. Hang it in the window, open up a curtain, let a little sunlight hit it, and they'll shine rainbows around the room. And you can really see these spectral colors. Just make you feel good all over to see the colors, right? Newton decided he wanted to have 7 colors. Maybe that's where the indigo comes from. They weren't even able to produce it on here. You know, red, orange. You can remember Roy G. Biv is your way to remember it. Roy, red, orange, yellow, green, Roy G. Biv, blue, indigo, and violet, right? Roy G. Biv is the way people remember it. It's just a tiny part of the electromagnetic spectrum. So we can only detect part of the electromagnetic spectrum. Way down here we've got gamma rays and high energy rays whose wavelength in nanometers, that's already 10 to the minus 9. So 10 to the minus 12 meters. We've got high energy rays that fortunately were protected by the ozone layer. Chlorofluorocarbons, which they used to use in hairspray cans and bug spray and other kinds of spray cans, used to use these chlorofluorocarbons, which are also used in refrigerators and air conditioning unit in your car and so on. These chemicals will go up into the upper atmosphere and destroy the ozone. There's now an ozone hole in our atmosphere, so it's more dangerous than when I was a kid to go outdoors. So in those days, though, we didn't worry about nuclear radiation. I told you about that. We weren't afraid of X-rays. But nowadays, you should be more afraid of these gamma rays than you had to be. We weren't afraid of getting sunburned either, which also causes cancer. But you're protected by the ozone and by the also protected by the Earth's magnetic field, which tends to divert high energy particles that are being emitted from the sun that will also fry you and kill you if you're out in space. Then there's X-rays. These are also fairly dangerous. Then there's ultraviolet. That's the stuff that's beyond the violet. It's called the ultraviolet. Some things will absorb light in the ultraviolet and give it back off in the visible spectrum, and so that's why you have black light shows. A white t-shirt made in cotton will glow under ultraviolet light. So ultraviolet light will stimulate the cotton, and the cotton will give off visible light so that then it, lights up and glows. So light shows, used to be in the days of acid rock and so on, people were really intrigued by light shows and black light effects and so on. Then beyond the red, in the infrared, you've got, well, it's beyond the red, so it's called infrared. This is where heat is, and night vision goggles can detect in the infrared, and some Sony cameras, and so there was a lot of talk about using Sony cameras in the dark to look through people's clothes and see them naked. And this is what they use in the airports to look at you to make sure you don't have hidden things in your clothes. So And so the night vision goggles can see a person in the dark because they're glowing, they're giving off heat, right? Everybody's burning a fire, breathing in oxygen and burning up compounds. You can see weapons like a motor vehicle, a tank engine that's glowing in the dark, but so you can see it at night, so military use. You can also shine infrared light onto something so other people can't see it, and then you detect it so that you can look around in the dark with an infrared source of light and also see it. Then beyond that is the radar and FM radio and television and AM. These things are long wavelengths that are going right through the building here and hopefully not harming us. Some of the microwaves, as you know, are being used for your cell phones. Microwaves are also being used, of course, to heat up water in your microwave oven and boil it so that you can cook with the microwaves. Whether microwaves cook people's brains or not, nobody knows for sure. Some people are afraid of microwave towers. Some firemen have been reading the news, been complaining lately that they don't want those microwave towers being put up right over the fire stations because they don't want to be exposed to all those microwaves coming out of there. Maybe someday you'll say, back in our day, we used to hold cell phones right up to our head, and this source of microwave radiation right next to the brain. Can you imagine that? Yeah, it's what people used to do in our day. So you can't see all that. If you could, why, we'd be able to look over, you know, and see the television tower going right through the building, because it's coming right through us, right? And light goes through windows, but it doesn't go through the solid material. So you can see through glass. Light comes through glass. Heat doesn't go through glass. Radio waves and television waves, they go right through the walls here, right? Microwaves, your cell phone works indoors. That means those waves are coming right through. You could see the microwave towers. You could look, if we could see them, we'd be able to look through the walls and see the microwave towers glowing, giving off all those, you'd see all these phones glowing. All the phones that are giving off their microwaves, they're sending, every so often they go beep, and they send a message, here I am, basically waiting for messages to the cell towers that are picking up the fact that your cell phone is turned on. But we can't see most of it. Our reality consists of what you can see in the visible light. Now, as you know, greenhouse works on the principle that light comes through the window, right, of your car, for example. Light comes through the window, is absorbed by the upholstery in the car and given off in the form of heat. And heat waves reflect off the glass. So the glass is like the walls are to light. Glass lets the light through, but it blocks the heat. So your car will get hot if you leave it out in the sun, as some people have discovered inadvertently by leaving their dog in their car or their child. There's a professor at Irvine. One day he was in his office and he heard a bunch of noise out in the parking lot, and he went and looked through the window and he saw the police smashing his window. He had forgotten that his wife said, take the baby to the daycare today, which was unusual, and he put the baby in the seat. The baby fell asleep, and he drove to work and forgot all about it and went up to his office and forgot and left the baby. And they had tried really hard to get a baby conceived. They'd gone through all kind of difficult medical procedures to conceive that child. And his wife said, take the baby to daycare, and he drove to school and forgot about the baby sleeping in the car. The car gets really hot. Fried the baby and killed it. Somebody had come along, called the police, and they smashed the window, but it was too late for the baby. And of course the earth is facing the same danger, because carbon dioxide is what they call a greenhouse gas. Your greenhouse works by letting light in, but letting the heat not out, so it warms up. So put a greenhouse out in the sun, it warms up inside there. You can raise plants in the wintertime, where it snows, where it's cold. Orange trees can be grown. So in Europe, they're sometimes called orangerie. It's the orange growing building with glass ceiling. And carbon dioxide is known to have the property that light can go through it, but heat doesn't go through it, just like glass. And humans are burning carbon compounds, increasing the carbon dioxide content of the atmosphere. So light comes down to the Earth, but the heat can't get out, and so it's bouncing back to Earth, so the global temperatures are on the rise and are warmer. You know, we're having, of course, 1,000-year drought here in California, maybe as a consequence of global warming. But another Republican state has just passed a law. They're not allowed to, employees of the state are not allowed to use the word global warming or carbon emissions or any of these things. They've been told by their governor and legislature not to talk about the problem because we can legislate it away if we can pretend that it doesn't exist. All right, so there's a brief discussion of light. Light has certain properties. Well, we might as well leave that up and say a few things about a couple quick properties of light. Light travels in straight lines in all directions from a source. And you can use that to create a pinhole camera. So light travels in straight lines. And if you're going to hang on to that premise, then you have to say space is curved eventually, because as Einstein noted, light appears to curve around a very massive object like the sun. One of the tests of Einstein's theory was being able to take a photograph of the sun during an eclipse and seeing stars that were behind the sun appeared in the photograph, showing that the light was curving around a massive object. So if you're going to retain the idea that light travels in straight lines, then you have to say that space is curved by mass. And we could use this to talk about a pinhole. So here's, you could take a sheet of tin foil or cardboard or something and poke a little hole in it. And we can have a source of light over here on one side. So here's point A and here's point B of a candle light. And then we can have a screen over here as our target. So we can do this in a dark room, and it's a useful little experiment for you to do. And the fact that light travels in straight lines, well, light goes off in all directions from point A, which is a point source of light. These rays of light don't concern us. This one goes and gets blocked. This one goes through the hole and ends up down here at point A prime. And point B is also a point source of light, so light travels in straight lines in all directions from it. And this is the ray that concerns us, because it gets blocked. This is the one that concerns us, because it goes through the hole and ends up over here at point B prime. And so the image in a pinhole camera is going to be upside down and backwards. We're going to use the pinhole model to represent the optics of the eye, even though that isn't actually what's happening. What's actually happening in the eye is that light is being refracted by the cornea mostly, and also by the lens that's in the eye. And I'll say more about that in just a bit. So in a pinhole, the image is upside down and backwards. And you can also do experiments like move the candle and see what it does, and you can predict the results based on the idea that light travels in a straight line. You can bring it closer, that makes the image smaller, and take it farther away, that makes the image less. And you can see that for any square inch or square measure, if you double the distance, it's spread out over 4 times the area. And so this results in the idea of the inverse square law for the intensity as a function of distance. So as you go farther away, if you double the distance, you reduce the intensity of light by the square of the distance. And the linear dimension is going to be directly proportional to the distance. So as you move this, it'll get dimmer and larger as you go farther away, because the same amount of light is being spread out over 4 times the area as you double it. All right, so that's the idea of the pinhole, and we're going to use that as our model of the eye. I've already mentioned this one right here is refraction and differential refraction. The way to think about refraction. So light is reflected. So another property of light is reflection. And the angle of reflection is equal to the angle of incidence if you had a perfect mirror surface. And then refraction is the idea that as light goes from one medium to another, it's bent toward the normal, which is a light at right angles. And for any wavelength of light in any pair of media, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant. That's known as Snell's law. All right, that's the principle of refraction. If you want to think about it, think about a muddy field. So here's our glass in the case of the refraction of light or water, or the Earth's atmosphere, which can refract light. But think of it as a row of soldiers marching along. So we've got a formation of soldiers, and they're marching toward a muddy field. So as they get to the field, this guy is affected first, right? And so then this guy's affected, then this guy. And so the whole formation is going to turn. In this case, they're going to turn a little to the right, toward the right angle. So if you could think of that as a metaphor for the refraction of light from a vacuum to glass, or from the air to glass to a denser medium here. You can think of it as soldiers marching on a well-paved road into a muddy field. It's going to turn the formation to the right. You can also think about the differential refraction for different wavelengths. The blue light is refracted more than the red light. The reason that the sky is blue, the blue light is being refracted the most. Why our sky is blue and why the sunset is red. Think about the soldiers with the short legs. They're going to have to take more steps into the muddy field than the soldiers with long legs, right? And so the short-legged ones are going to be turned by more. And indeed, that's the case, that the violet and the blue are the shorter-legged soldiers, and the red are the longer-legged soldiers. And so the greater wavelength, the smaller wavelength or higher frequencies light are the ones that are bent by more. The bluer light is refracted, the purple and blue is refracted by more than the red, the longer wavelengths being the red type of light. All right, well, I guess I can add one other property of light. So this is reflection. This was refraction. We can talk about a lens. So if I had a prism with light coming this way, it's going to be refracted like that. If I had a prism pointed this way, light is going to strike it and go that way. And if I shape the two prisms just right and carve my lens according to the exact right formula, then parallel rays of light will all be brought together at exactly the same point. And this point where the rays of light are all brought together is called the focal point, and this is called the focal length of this lens. And the idea of a lens, of course, those of you as kids probably got a magnifying glass at some point. Maybe it wasn't perfectly carved, but you could go outdoors and measure that. You could find an ant crawling along or a little poor pill bug, and you could focus the rays of the sunlight onto them and fry them, start fires with the lens that way by concentrating. If you had a big magnifying glass, concentrating this much sunlight down onto a small spot, why that much sunlight is strong enough to start a fire, to fry the ant or the pill bug and set fires. If you were out in the woods somewhere and you had nothing else, if you had a magnifying glass, you could start fires. You wouldn't have to rub wood together to start your fire. All right, so we're going to have actually a lens and a cornea in the optics of the eye. here's our diagram from Calit. Different versions of this in different editions. And I'll go over some of the features of the eye. They've got the light crossing there, but we're going to model it with the light crossing. We're going to put every ray of light going through a point on the front of the cornea will be a better approximation. What he's got right there is a pinhole model where the pinhole has been put into the spot where the lens is. What's actually happening is the light is coming off from every point and it's hitting this surface here. The front surface is the cornea. It's not properly labeled in the diagram. This point should be touching right here. This is the cornea, not this. All right, so the cornea is that out there on the front surface. There are muscles that are not shown, that are going this direction. So they're running actually left to right in this picture, in this direction. And when they flex, they can change the actual shape of the lens. And that the ability to change the shape of the lens allows you to focus at different distances. In a camera, so those of you who had an old-fashioned camera, the lens moves forward or back. Nowadays, you have cameras that have a lens that's built in that moves forward and back on their own, or computer software that corrects for the fact that the image is out of focus, depending on how far away it is. So the cornea is doing the bending, and some of the bending is being corrected by the lens, which is sort of changing the focus. So we have refraction at the cornea and refraction at the lens. Cornea is separated from the bloodstream, which is both good and bad. It's separated from the bloodstream, and that's sort of good because if you damage your cornea, you can get somebody else's cornea. So a motorcycle rider who doesn't wear goggles is going to get damage to their cornea. Things are going to hit the cornea and damage it. Maybe a particle will hit it and cause an infection, damage the cornea, which will make it so the person can't see properly. But another motorcyclist who doesn't wear a helmet might contribute his cornea by getting into an accident, dying, and having marked that he's willing to contribute his cornea. They'll transplant the cornea from this person to that person, stick it on there, and the bloodstream does not go, blood does not go to the cornea, so the body won't reject it. So you're able to transplant cornea from one person to another with a very low risk of, as you know, transferring blood. You can kill a person with the wrong type of blood, and when you transfer organs from one person to another, if you don't have a good tissue match, the body will reject it. The body's own immune system will attack it and reject it. But the cornea can be transplanted. If you get a disease of the cornea, that means you can get a transplant to replace it. So diseases of the cornea can be corrected that way. Lenses also, we can make an artificial lens and replace a lens. In the case of the lens is living tissue. It's sort of isolated from the bloodstream. One of the reasons these are isolated from the bloodstream is, as you know, blood absorbs light. It's got a pigment in it. The pigment even changes color depending on how much oxygen it's carrying. The blood that's oxygenated looks redder, and the blood that's less oxygenated looks bluer. That's why they draw the arteries and veins as red and blue to represent the change in color in the pigment of the blood. But there isn't any blood in here in the lens. And that's sort of good and bad. It's good because the blood would block the light coming in. But it's bad because if there's a problem with the health of the tissue, the blood can't get to it and correct it. And so a person with diabetes, for example, their lenses will begin to die and rot, and they're high candidates for having to get their lenses replaced. So a person with diabetes, they have a lot of problems, a person with diabetes, a lot of tissue damage, but among them is they may begin to lose vision. Again, for other reasons they may lose vision, but they may also lose vision because of the lens, but that's one that can be replaced, in which case they will often do it with an artificial lens. The rods and the cones are mislabeled in this diagram. They make it look like the rods are the red and the cones are the purple, but there's actually rods and cones all the way around here. Higher density of cones around in here near the fovea. Now when you're looking directly at something, it's being projected right onto the fovea. That's right behind the point where you're looking. The diagram here, it mislabeled where the blind spot should be. I mean, I think Khaled had trouble communicating with his artists in general. The optic nerve comes into the eye, carrying, well, the optic nerve leaves the eye, let's say, carrying axons that are coming from ganglion cells, going to the optic nerve and going out. Blood vessels are coming into the eye, carrying blood to the retina. The retina is 3 layers of cells deep. We're going to review that probably today or next time, if not by the end today. The image is upside down and backwards, so you should remember the fovea, and we're going to do an experiment on the blind spot coming up. All of this structure is called the retina all the way around, and it consists of rods and cones. Okay, so I've talked about all the major features in this diagram about the eye. Now when you look into somebody's eye, what color is it when you look in through the pupil? What color, when you look right into somebody's eye, do you see? Anybody looked into somebody else's eyes?
Other than their eye color?
What's that?
Other than
Well, there's the iris. That's the colored part, brown or blue. But I'm talking about looking right into the pupil. What color do you see when you look at the pupil? All right, so it looks black. You know why it looks black? Because your head is blocking the light that would allow you to see in there. If you shine a light in there, now most of you have probably seen the results of this. If you shine a light in there, what color is it actually in there? Take a picture of somebody with a flash attachment right near the lens, right? With a camera that has a flash attachment here and a lens right here. What color do you get? You see those little demon red eyes. That's what it really looks like in there. Okay, so if you can see into somebody's eyes, it looks red in there. When you take that picture, that's the picture you get. How do you avoid getting that picture? Because the person looks kind of like a little demonic look, you know. Well, one thing you can do is you can just Photoshop and blacken it out and get rid of it. The other thing you can do is you can have a double flash. So a lot of cameras have a double flash. The first flash goes off, makes the person's, you know, when there's bright light, the irises will close and make the pupil smaller. So you have small pupil, and then the flash is just far enough away that the light doesn't go in, that the camera is still blocking the light that goes in there so that you don't see the red dot. So the double flash method is one method, but then you get a picture of a person with little small pupils. And a person, when they like something, their pupils get bigger, and when they don't like something, their pupils get smaller. So the person looks kind of pissed when you get a picture like this. It doesn't make a good portrait to have the small pupils. Now the old-fashioned method, they had a big, you know, a source of light. The flash is behind the photographer, and he had a big camera, and his head and the camera and everything blocks the light that goes in there, and his flash attachment's way over here. So you have an indirect flash that's far from the source of light. And when you go to the doctor, they want to look in there to see if you have a herpes infection or if you've got a tumor developing or you have damage to your retina. People damage retinas all the time by such stupid things as, like on New Year's Eve, they like to aim champagne corks at each other, shake up the bottle of champagne and go, ha ha ha, pow. About 130 people a year get their retinas detached that way every New Year's Eve, you know. Not counting the people that shoot guns in the air, and occasionally some kid gets hit by a bullet that comes down from one of those New Year's Eve celebrations of shooting guns off. But about 130 a year get because those people usually aim it at each other, the stupid people. Some boxers have had this happen to them too. The person throws a punch with the thumb out, hits him right in the eye in just the right way. Sugar Ray Leonard was a person, had that happen to him. He wasn't able to box for a while, but he did a laser surgery, and he was able to get a license in some state or other, like, I don't know, Nevada maybe, which will license just about anybody to box. So the doctor wants to look in there. They use an ophthalmoscope. How many of you have had such surgery, not surgery, but such an examination done? You probably gone in and had them, they should look in there to see what's going on. They can see various things. They might see an early sign of diabetes. They might see damage to the retina. They might see other things when they have that. And pay attention to it next time because you're going to see the shadows of the blood vessels in your eyes when you have that examination done. What's it look like when you look into the eye? We'd like for you to go where it says perceptual demonstrations. Here's looking straight in. So here's what the doctor is going to see when they use an ophthalmoscope to look in there. Here's the fovea over here. So the fovea, here's blood vessels coming in out of this is where the blind spot is. Anything that's projected there disappears, so you can't see something if it's projected onto the blind spot. So I want you to do the experiment with the blind spot, which is, you can have a dot. I forget how it is in the homework. I have a dot. Let me make it up higher here. A dot and say a plus here. And this will be the independent variable of your experiment. We'll call this S, the separation between the dot and the plus. If I look at the dot with my right eye, closing my left eye, so I look at it with my right eye, looks here, I can now back up, and at this distance, the plus disappeared. So I'm looking at the dot with my right eye, the plus has disappeared at this distance. And this is the dependent variable. So the independent variable is the separation, and so you will manipulate it. You can just draw one on your notes right now, about 3 inches apart. Hold them horizontally, move it, looking with your right eye at the dot. You'll be able to make the plus disappear at some distance. Then you will increase that distance or decrease that distance. The farther apart they are, the farther away you'll have to be for it to disappear. So if I want to make this plus disappear, this is the distance. If I want that plus to disappear, that's the distance at which it will disappear. So the outer plus, and now the inner plus. So that'll be the dependent variable. So your independent variable will be S, the separation. So here's another different level of S. Call that S1 and that one S2. And your dependent variable will be the distance for the plus to disappear. Now you'll also notice, if you want to make the dot disappear, you have to look at the plus with your left eye. So I can make, if I look with the plus with my left eye, I can make the dot disappear. So part of the assignment is to work out for yourself, why will the plus disappear if I look with my right eye here, but not with my left eye? And if I want to make the dot disappear, I have to look with my left eye at the plus to make this dot disappear. So why do I have to do that with the two eyes? Y is the distance directly proportional. Y is D. Let's call that D is our distance. D directly proportional to S when you do that. So this is the color, and this is the red that you see when you take those photographs with a flash attachment right near the lens. Now, the rods and the cones, here's a diagram from Calit of trying to illustrate a theory. The diagram's a little bit incomplete. We've got rods and cones up here, bipolar cells, and ganglion cells, and the ganglion cells are the ones sending their axons that go out through the optic nerve. All right. Blood vessels are coming in, and blood vessels are running through, bringing energy to keep these cells